the ideas behind, and I will give you the main points. And in the notes you can find details. So today I will be less explicit. The first three lectures have been extremely explicit, very slow, because I've done these lectures many times before, and I always find that it's in the beginning that people get confused. So by now you have a faint idea of what kind of manipulations we perform. And now I will give you an outlook. I will also mention a few conjectures I have where I believe mathematicians can work. And I intend to work these notes further out because I've had so many questions from people in the audience which were good questions, and I try to keep note of them, and I will put these questions in the notes and I'll put them on the blackboard. So you will probably see some of your questions in the final notes without due reference at work. Now, I want first to finish the geometry of superspace. The way I have set up these lectures was very lowbrow and elementary. So I'm discovering things. Of course, I know where I'm going, so I'm tilting the deck. It's not that it happened in a very chaotic way in reality, but I've streamlined history and rewritten history in a way that everything is logical the way I present it. It never is, of course, in reality, but that's the way I did it. So I began, if you may remember, by saying, suppose we have two kinds of sets of particles, bosons and fermions, and we have commuting fields for the one class, and I took the simplest example of a commuting field. A space-time, I took one-dimensional time only, and later I will discuss in the point two higher dimensions. And I had a fermionic field which was really a Grassmann variable, and we discussed at length what it means to have a Grassmann variable. But I think by doing the manipulations you discover in general the definitions better than giving them a priori. I have given them a priori, but combined with working with them, I think you should get a good idea. And this Lagrangian, if you integrate it over time, it's called an action. It was invariant under these infinitesimal variations. We went through the proof, and the parameter epsilon was a constant. And that was the first model, not historically, but in the lectures, of rigid supersymmetry. Rigid meant that the parameter epsilon is constant. That was a definition. And now I wanted to rewrite that model in superspace, and an active creation, intelligence, imagination, or a hunch, or whatever, had to occur. So the idea was that in addition to t, the time coordinate, I introduced a Grassmann time coordinate. So I have two time coordinates, a bosonic time coordinate and a fermionic time coordinate, and commuting and an anti-commuting. Now this I cannot derive, and I gave you arguments why you still might have gotten there. For example, everything, if it is commuting, has an anti-commuting counterpart, so why not for coordinates? That's the logic behind this. I don't know of anything more compelling. So it is an idea. I write it in very small letters because I've tried to do everything logically, but here a spark had to happen somewhere. The spark was done by two physicists in Trieste, Solanus, Rasdi, who invented this idea. Now, and then it's natural, fields depend on time, so if you have this space, it's natural to have fields which depend on these two coordinates. But we went through the discussion that this is a Grassmann variable, so the square of this thing is 0. We explained it at great length. So if I make a Taylor expansion of this thing, I only get two terms, term without theta and term with theta, and explained why you needed the I. That was, I wanted psi to be real, and therefore to make this real I needed the I, and then this whole thing was real. So this we call a superfield. And then the next thing, the way I present it, and of course other people do it differently, I just want to retrieve these two laws, which I had derived before from really first principles. I want to re-derive them in superspace. So I'm now saying the variation of the big field phi has to have a certain rule, and the rule I say there is some operator, which I haven't specified yet, I call it Q, and there's a parameter epsilon, because after all I had epsilons here. And then I want to commutate with the field phi, and I explained to you last lecture that I sometimes write when this is an operator which can act on phi and past it. If I want to say only x on phi, I write it with a bracket around it. So if there are differential operators in here, then they're only supposed to act on phi, not beyond. That was a notation. There's no thing to be understood, it's just a notation. Now it is now very simple. By writing the most general Q you can down, and the Q I take a linear derivative, dd theta, ddt, and any coefficients in front. And then when it acts on phi, for example in ddt, when it acts on phi, it can act on the phi of t, and you get phi dot. But it can also act on the lambda of t, and then you get lambda dot. For example, if you have the dd theta operator, when it acts on phi, then it can only act here. And I explained with you that dd theta acting on theta is 1. That is just like ddx acting on, ddt acting on t is 1. So, doing this algebra, you can then fix the coefficient in front, and the answer is this. Now, I propose not to do the calculation, it's completely straightforward. But with this expression, this differential operator acting on phi, I say then that this delta phi, I write it also as delta phi of t plus I theta delta lambda of t. And if you then substitute for delta phi of t this rule, and for delta lambda of t this rule, and on the other hand, on the left-hand side, you work out these derivative operators on this field, then the left-hand side becomes equal to the right-hand side. So I have now transcribed my results of t-space, ordering t-space, into superspace. Yes? Yes. Notice there's no t-dependent. The reason is, at this point, we'll be very deep in a moment. At this moment it is because I just fit it. I wrote the most general thing. I could have written here a function of t in front, but requiring that this thing is equal to this thing, I discover that there is no t-dependent things in front. So this is calculational outcome. And, you require that the left-hand side is equal to the right-hand side. The right-hand side we knew from lecture 1. The left-hand side, this is unknown, but phi is known. And you can just solve this equation for q. Now this is the answer for q. I also would like to retrieve the action. Now the action was the time integral of this, but when we are now in a space with a commuting and an anti-commuting time coordinate, it is natural to introduce an integration over dt and d theta. And our third lecture discussed the integration over theta. It was what we call the BRST integral. It's well known in mathematics, it's also well known in physics. In physics it's well known because half of the particles we have are fermions, and when we describe them in path integrals we need the BRST integral. And the other half of the particles are bosons, commuting fields, and there we have oceans ordering Riemannian geometry. So in physics it's very beautiful. Half of the integration is Riemannian, half of it is Brownian. So we discussed this integration. Now,
where's the lambda?
Well, this is a big phi, huh? A big phi has in it lambda. Oh, thank you very much. Absolutely. So please, thank you, of course. So if I would have written, maybe thank you very much, and let me do it also here. Now you see here. Don't kill me. So, this thing, when I do the t integral, I get an answer. I now want that the expression I get for s is equal to the expression, this expression for s. Now, I know what d theta means, so I can first do the theta integral. And then I want whatever I get as a t integral to be the same as this. And without proof, I'm telling you at this moment, and the geometry will come again, that the answer to this problem is this action. It looks a bit similar. Here you have phi dot, phi dot. Here you have a ddt on phi that looks like phi dot, except the ddt is now not on the little phi, but on the big phi. But here you have a new operator. You would have expected another ddt. Now the dimensional arguments again, which explain that you need a capital D here. And they are done in the notes, but I'm not going to do them now. So I need to move a certain way, so I cannot everything really do. Now this operator D, at this point, I define it such that I retrieve this. So just like I computed Q by requiring that the transformation rules match, I define D such that the actions match. The original formulation had an action and transformation rules. The action leads to a new object called D. Transformation rules lead to a new object called Q. Now we're going to say in a moment that Q has something to do with left multiplication of group manifolds, and D has something to do with right multiplication of group manifolds. And because left and right multiplication commute, if you know this, you anticipate that D and Q anti-commute. And in fact, if you work out, this is totally straightforward, and I mentioned it last time, I did the QQ anti-commutator, but D and Q anti-commute. Conversely, I want to explain a bit the things behind it. Conversely, and this is, I was in Trieste when they did these things, and I know how they thought, and this is really how it happened. They had an idea of coset manifolds, but everything wasn't so clear in the beginning. And somewhere in their calculations, these two people noticed that this algebraic relation holds between the Q they rather early found and the D they found somewhat later. And then they had this great idea that something, if it commutes, has to be an origin for commutation, and that is left and right multiplication, which of course commute. Now, so at this point, from my logic, I started with this lecture 1, and I have, for no good reason, introduced a theta, that was a spark, and I've now found transformation rules in superspace and action in superspace, and these things are just bookkeeping, more complicated, exactly the same content as this. I've introduced a theta, but after you integrate over the theta is gone. So what is the bother of introducing a theta? Yes? Yes.
Last time you indicated about
Yeah, I have at this point, this is rigid. The question is, where is lecture 2? Lecture 2 has disappeared through the cracks in the floor, because lecture 2 dealt with supergravity and all these beautiful anecdotes, and now it's gone. Well, it's not easy to say that. Actually, this is rigid supersymmetry. There is also a superspace description of local supersymmetry. And then we get diffeomorphisms in the bigger space, which has Dennis already anticipated. So then we get the whole formulation of diffeomorphisms, except that whereas previously you had one coordinate T, now you have a T and a theta, but all the usual rules go. For example, the volume element will then be the determinant, in this case the super determinant. Beresinian, some people call it, depends whether you're from the east or the west. And the super determinant will enter, and so all the rules you know from geometry, from diffeomorphisms and so on, carries over. But in the moment I'm at rigid supersymmetry, so I'm not yet doing diffeomorphisms.
How complicated will they actually be?
I can write it down. Let me write the answer down, then you have an idea. The action, it is still in dt and in d theta. And then I need a super determinant of, then there is a superfield bind. It is a 2x2 matrix, where this index lambda stands for T and theta. But this is a tangent index. This is a base manifold and this is a tangent index. This thing, and you have to multiply this, let me write times, and then instead of dt, you get something like the two matrix elements E. Now, and will be also T and theta, but to indicate that their tangent indices, I write a bar over them. So you have to distinguish between a tangent and a base manifold. I think you know that far better than I do. So then here T lambda, and then you get here E lambda phi, and then here E theta lambda, E lambda phi, where these are the superfield binds. This is the determinant of that 2x2 matrix. These are the old fields phi we already had. And the lambda consists of a ddt or the operator q, d, which was dd theta plus more. So here's the answer. Now, it's beautiful. It needs much more talk. And I have very limited time. I thought that 4 lectures was far enough to tell you everything about what we've done the last 30 years, but it didn't work. All right, now, so I'm now at rigid, not local. There's local, here's rigid. And this was rigid. So I got so far. Now I want to give you the mathematical interpretation of all that. So the way I derived it, once again, I pretend I know nothing. I just follow my nose. Here I did something, I couldn't say why. One day I awoke, I said, why not? But the rest was deducted. But there is a whole geometry behind it. Now this, I now have to make enormous leaps in that field because it's a very large field. Some people like these days to begin with an abstract algebra. Then they introduce an abstract operator Q, or a generator of an Lie algebra, a superalgebra really. The representation of Q in terms of differential operators is this. It's only a representation. It's like a rotation group. You can write it in terms of derivatives x d dy minus y dx or so. But the more abstract thing is an abstract Q. And there's a second thing, H. The representation of H in terms of derivatives will be I ddt. In this translation generator, and I want it to be anti-Hermitian, maybe I should not have called it H, because H is used in energy and physics, and then it should be real, but no, actually, it is real, because ddt was anti-Hermitian. Last lecture I proved that. And I times something anti-Hermitian is real, so even right. Now, this is the superalgebra on which this trivial model rests. You can check that the Jacobi identities are satisfied. Certain things. It's very easy to do. You have a lot of zeros here. So it is not a simple superalgebra. It's a non-semi-simple superalgebra. And the definition of non-semi-simpleness for superalgebras is not at all obvious. In mathematics, I'm aware of about 5 definitions of what semi-simple means, having to do with the Cartan metric or ideals, and there are lots of them. And historically, by the way, you probably know better than I. In mathematics, the correct definition for simple Lie algebra or semi-simple also went through a lot of vagaries before people found a useful definition. Mathematically, you can choose any definition, of course, as long as it's not internally inconsistent. But sometimes you have a definition which covers a few cases, but it can't cover cases you also might be interested in. So your definition was not the most appropriate. But by trial and error, people found in mathematics the good definition for semi-simple. Now here too, it is not at all obvious. You take these 5 equivalent definitions of ordinary Lie algebras, and you see which one is most appropriate for the extension to the super case. And in that way you find it. But I'm not going to discuss that. I have a concrete superalgebra, so I don't care. This is the thing I'm interested in. And now I'm going to follow Cartan. Now Cartan wrote a number of books, obviously, about Lie algebras, and Cartan, subalgebra, all of it. But he also viewed these Lie algebras in a very physicist way, I would say. He having action of a group on a plane, so I would say this is a transformation group which acts on a carrier space, the usual notion in mathematics. And I'm now going to act not on a plane but on exponents of something. So here I'm going to define exponent theta q plus th. H was Hermitian, so I write an I to make this anti-Hermitian. But theta and q were Hermitian. I went through the proof last lecture, number 3, that q was Hermitian. Theta was real. So then this thing is anti-Hermitian, because you take Hermitian conjugate, you do like this. But if you bring them back, they're both anti-Hermitian objects, you get the minus sign. So this is anti-Hermitian, anti-Hermitian. And it is natural to write exponents of something anti-Hermitian, because then you get something unitary. Now, all this generalizes notion you already know from ordinary mathematics, because there are only Grossman variables in the game. Here, theta is a Grossman variable. Q is an abstract object at this point. If you want secretly to think, or when it gets too abstract, that it has this representation, you may do that, but at this point, I treat it as something abstract. H is something abstract. Again, secretly, you may think of I ddt. And T is just a real coordinate. Now, this is familiar, and I'm sure it's familiar to this audience. So. Now, this is a group element associated with this Lie algebra, superalgebra, by which I mean I can take products of 2 such elements. It is again an element in the set. In order to do that, you have to treat this as you usually do with commuting with Lie algebra generator. So if you bring 2 exponents together, there is an algebra also called Baker-Campbell-Hausdorff. Maybe people know that very well. So I can bring these things together. I always get the question, yes, this is impossible. You can't write exponent of something anti-commuting. But notice, theta times q is not anti-commuting. It is as if it's commuting. More precisely, it lies in the even part of the Grossman algebra. So my usual algebraical tricks go isomorphically through when I have this object. I'm aware that this object, here it is. Now I'm going to multiply from the left by this thing. Epsilon is this epsilon. Q is the same Q. Because I have Q and H here and here, if I do Baker-Campbell-Hausdorff, I need commutation relations for epsilon Q and TH. If I do that, I get first the sum of the two exponents. But then I need starting doing commutators. Now, there's only one non-trivial commutator. It is the Q is the Q. You can see that from here. Q is an H, but this and this is 0. So OA is a little, it is small, like delta T. It's a little increment of time. So it's a real number. Epsilon is a Grossman variable. Real. But now I need 1/2, and then the commutator of epsilon Q, and here theta Q. Of course, that's the only thing that remains in this infinite Baker-Campbell-Hausdorff theorem. If you don't believe it, go to the library, look on the Baker-Campbell-Hausdorff, open the book, and it's so long, the formula, and notice that all other terms cancel. No, at this point it's a commutator. You're ahead of me. Yes, exactly. You already said what I'm going to say now. I can't use this yet because I had anti-commutator of H here. But you can check by writing it out or understanding it or whatever that this thing is also equal. Now I can pull the epsilon to the left. I can pull the theta to the right. But if it moves past the Q, you pick up the minus sign. So the minus sign I'll write here. And then I'm left with an anti-commutator of two Q's. Now there are two terms on the left, and there are two terms on the right. And let's work them out. I see some puzzled faces, so let's do it. Epsilon Q, theta Q, minus theta Q, epsilon Q. I claim that equal what I have here. Now here I have minus epsilon Q, Q, plus Q, Q, because the anti-commutator is twice the thing itself, times theta. Now notice, it's maybe good I do this explicitly. You should not, at this point, view Q as a differential operator, because then it would act on theta. At this point, it is an abstract object, Q, and it, at this point, lives in a different space, if you like, from epsilon and theta. It's a generator which doesn't act on the coordinates, if you like. So you could think of Q acting on fields and epsilon theta and on fields with coordinates. In any case, I can now move this theta past the Q, and pick up the minus sign, and then I have the first term. Now this term, I can move the epsilon in front here, then it moves past two anti-grating objects, so no change in sign. Then it sits here. And then if I make the theta going all the way to the right, it moves also past two anti-grating things, Q, no change in sign. So I get a second term, which is exactly the same. So indeed, this is equal to this. But now I can work this further out. This becomes now exponent epsilon Q plus IH plus theta Q plus ITH plus, now I use QQ as H. So I'm going now to replace QQ as H, and then I get minus I epsilon, and H and theta commute, so I will put H to the right of theta. And now this is very interesting what happened here. This is a little calculation I did, but now I'm going to interpret this calculation. Where did it? Oh, there's a half here. So I need a half. There shouldn't be an I. Why did I write an I? Thank you. Let me do it again. So I got a half minus epsilon So I think I got this. But this I can write as the exponent of something times q, and I'll write in a moment what it is, plus something else times h, by just combining terms. Now, what is multiplying q? First of all, there's a theta. There's also an epsilon. And that's only the q terms I have on the board. Now for h, I have I times, I'll take the I out, and I have a t. I have here the a, but I have a third term. It's this. Now minus, I'm going to write as I times I. One I is in front, and the other I sits inside. So we get plus I, epsilon over 2, epsilon theta. Now Cartan did this, but he didn't do it with thetas, he did it just with ordinary group coordinates. But I'm just using the same tricks. And now I interpret this as he did, that this is an action of the group on the coordinates. In my case, on the coordinates t and theta. So I'm now going to say the action, which I ended out, I'm now going to use the same notation as for fields, but I'm now doing it on coordinates. Delta theta, delta of epsilon on theta. The action, if you have a multiplication with an epsilon q term from the left, let's say a is 0 in this case, then the result is that theta gets replaced with theta plus epsilon. So the increment of theta is epsilon. So delta theta is epsilon. Delta epsilon on t, I read it off from here what it is. If epsilon is non-zero, a or 0, then I get t plus I over 2 epsilon theta. There are also transformation.
Excuse me, what happened to A?
To B. Oh, A, thank you. No, no A, sorry, like this. I can also, yeah, epsilon q on the curve. I can also do this if I had multiplication by AH and not an epsilon term. So then I get delta A on theta is, oh, what is that? 0, yeah. So translations along the time axis do not change the other axis. Very natural. Delta A on t is A. T plus A. That's natural. That is when you move along the axis a little bit. A going from t to delta t. I call delta t A here. So I would say this is very natural. This is all natural. That is when you have a plane x and y and you move along the x-axis, then y doesn't change. And y is called theta here, but that idea is still there. This is, of course, a very interesting result. Postulating this algebra, I'm going in a moment to say how I would derive this algebra, but believe for a moment, postulating this algebra, we've seen that the interpretation of rigid supersymmetry is that it is in translation along the anti-commuting time coordinate, theta into theta plus epsilon. This is the big surprise. Now, little anecdote. Before I entered this field, there were other people who looked at things. And they loved Riemannian geometry. He called it super-Riemannian geometry. And they said, everything you know from ordinary Riemannian geometry, you just put on a theta and an epsilon, and the rest you keep as it. And so we said, okay, in rigid supersymmetry, that's very easy. You have a t and a theta, and then you translate one and the other. So what did these people do? Delta A on theta was 0, but they also said delta epsilon on t is 0, because they said translation in the theta direction shouldn't change t. Now here, however, we found from the algebra that was because q equals h. This relation was the origin from here. So you see, if you would have a completely abelian algebra, then things are as you naturally would expect. But having a non-abelian feature in the algebra leads to this very profound term. Now this term has a big meaning but I derived it like this. Now this, in modern mathematical language, I would call a representation of the algebra in terms of the coordinates. So now two representations. I have one representation in terms of fields, phi and lambda. I have another representation in terms of coordinates, theta and t. The representation in terms of fields is linear, because one field goes over in another field, but here another field goes over in one field. The representation in terms of coordinates is nonlinear. One coordinate goes over to another coordinate, but the other coordinate only goes in the parameter, not the first coordinate. So this is a nonlinear representation of this abstract superalgebra. This is a linear representation of this algebra. That is the reason, that is why, in the early days, everybody was confused about degrees of freedom. The linear algebras, that goes the way you expect. The representation of coordinates, not at all. So one should not first more or less understand this and then think, well, the same applies here. The fact that it's nonlinear makes counting degrees of freedom completely different. I'm coming back here to counting degrees of freedom.
What's the relationship?
I would say, well, there is one. So, ask questions, but they are, of course, I didn't plan them. The relation is this, that you can consider a finite transformation of the field, the big field phi.
No, but it's not part of your problem.
Well, it's one line.
No.
Yes, it's one line. T prime, epsilon prime is phi of t and theta prime. Phi of t and theta. So if I write phi prime infinitesimally as phi plus delta phi, and I write t prime as t plus delta t and so on, then this is the relation. Knowing delta t and delta phi, delta t and delta theta, you can work out what delta phi is. Conversely, knowing what delta phi is, you can work out what delta t and delta theta is. Now, this is very deep, and we're going to go much deeper mathematically. You intertwine coordinate representations with other representations. Physicists...
You're saying the axion field is produced by the axion.
Exactly.
But I am confused.
You said it. Physicists call this a scalar field, but it's
It should be twice, it should be consistent.
Okay, that is, let me quickly see. 2, yes, you're even right. I'm sorry. In the notes it is 2. So I write 2, that means that here the half goes away, here the half goes away, and here the half goes away. Thank you very much. Now, this transformation of the coordinates can also be written as delta t is epsilon q acting on t, and delta theta is epsilon q acting on theta. Now I have a representation for q in terms of coordinates. These rules I derived can also be written like this, and then this q is this differential operator. So now you see how I could have gotten this from first principle doing this, but then I would have had to postulate this. So how do people in physics get these superalgebras? 2 ways, as always. Either you sit down, you write anything you feel could be possibly there, and you start trying to satisfy Jacobi identities. That way you can find lots and lots of superalgebras, and then you try to see the physics of them. Another thing is that you have concrete models, and you follow the way I just did. There were classification schemes for superalgebras written down. Originally, of course, people missed whole classes, but by now it is believed that for the simple superalgebras we know all there is. As in order mathematics, there's no complete classification of non-semi-simple superalgebras. There's also not a complete classification of non-semi-simple orderly algebra, so we're not as bad as you might think. We're equally bad. Now, so this was the geometry behind it. The operator D I'm not going to go through the steps, I'm just going to say it. D is obtained if you put this vector on the right. You do the same steps. Then again, you get an action on coordinates, and you can write it as an operator which you then call P. And it turns out that only this sign is different. And the reason it is different is, of course, that the commutator came from the other side. That means, compared to the original commutator, you have a different sign. Now I want to terminate here because there's so much I want to tell you, so short time. But here isn't. Now, there is a way to derive all this, and I've decided not to do it in the lectures because I have no time. But there's a canonical formula, a Hamiltonian approach. It's all explained in the notes. So with every variable, which I can call phi at a given time, lambda at some time, there is associated a conjugate variable called canonical momentum. This goes back to the early days of quantum mechanics, where people, first you can write down Poisson brackets. Now, mathematicians know Poisson brackets, Poisson invented them. And then physicists realized that Poisson brackets describe also quantum physics. All you have to do is, instead of what you have on the right-hand side, you multiply on the right-hand side of the Poisson bracket by I h bar. I is a very deep story, I have no time to tell you. Beautiful and close. H bar is called Planck's constant, and if H bar goes to zero, you're back in classical physics. If H bar is non-zero, you're quantum physics. So there's a natural transcription from Poisson brackets to commutators. The one who did this was Dirac. He was the one who realized that Poisson brackets can be generalized in this way. Before him there was Schrödinger, well, there was really Heisenberg, and these people wrote infinite matrices, and they worked. And later Dirac not only introduced Poisson brackets, but also showed that this matrix approach was equivalent to a later approach which is called the wave approach of Schrödinger. Little historical anecdote. The Dirac has a long record of good things, also bad things. Now I want to go to step 2, higher dimensions. And I have to be brief, but I will tell you the ideas. I had here 1 time t. You may think, can I not have more? Yes, you can. For example, if I would go to one space 1 time, I would have t and x as Bose-Only coordinates. In that case, you need 2 thetas, which I will call theta 1 and theta 2. So then I have a 4 coordinate space. You may think that each time has as many thetas as t's. And in fact, in 4 dimensions, that's even true. If you have t, x, y, z for ordinary coordinates, length, width, height, and the time, then you still write 4 thetas. But if you go in higher dimensions, you need more thetas in general than t's. So I only mention this, I'm not going to explain why. There are perfectly good reasons for it, but I have no time. The highest dimension where you can go, as far as we know, is 11 dimensions. Then you have 1 time and 10 space coordinates. And then you need 32 thetas. You may notice that 32 is 2 to the some power, and that is because the representation of the Clifford algebra has that dimension. But I will not go into it. Lowest power of 2. And in fact, in dimension d, the answer is the number of thetas is 2 to the power d over 2 on j. So when I'm 11 dimension, d over 2 is 5 half, on j is 5, 2 to the power 5 is 32. Yes. So that's the rule, but there's a reason behind it. That rule is representation of Clifford algebra. Because this Mr. Dirac also took the square root of the diagonal version, and that's where the Clifford elements enter. So that's the reason. Now, this 11-dimensional theory can only exist with local supersymmetry. Amazing. Of course, you can make that local parameter constant, but it still can also be made local. So the higher you go, it's like in mountains. The more animals die. And on the top of the mountain, we have 11-dimensional supergravity. All rigid supersymmetry has died in the lower, it's like trees and lower things. And that 11-dimensional supergravity,
What do you mean the rigid ones die?
you can't write it. Yeah. I said you can certainly take the local parameter constant, but then it's a special case of the local case.
What do you mean it dies? What dies?
What I mean is you cannot write a model without gravity in 11 dimensions, or without a local gauge field of supersymmetry. Let me be more explicit. This model was a rigid model. We could make it local by adding gravity.
Oh, I see. No truncated.
There's no truncation. Very good, yeah. I must remember that word, but that's the technical term. No, that's a very good point, because many people thought, well, you just drop a few terms and it still works, but it doesn't. There's only one model in 11 dimensions. At least that's what all my colleagues always tell me. But of course, I've always been dreaming about an extension. So here comes my first conjecture. Nobody has been able to add a cosmological constant to this model. What it means in this model is, here you cannot do it either. You can, cosmological constant is something proportional to h, that h field, in the local case. So here, in higher dimensions, it's the square root of the determinant of the metric, or the determinant of the field line. If you write such a term down, you try to make it locally supersymmetric, precisely using the steps I did in lecture 2, and really that's how we do it all the time. So you don't get kindergarten, but this is the real technical things. It doesn't work. For 3 steps, that procedure which I explained to you works, and then it doesn't work. So here is an example of something that you seem to be on your way, and most people in the field say, oh, I did 2 steps, now it works. But no, it doesn't work. And it's only when you then do the next step you discover that. So some people who always write 1 step and then they write plus dot 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 dot, then they say dot 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 is wrong. So now the question is, what is the meaning of this? And this is a disaster. Let me now say something about physics. So I mix now completely physics and mathematics. You cannot do this. There was an idea, and this goes due to a mathematician called Kaluza. Kaluza was a mathematician of Kaliningrad at the time. It's now Stony? Königsberg. Oh, he was in Königsberg. Now it's called Kaliningrad. My logical coordinates. Thanks. And he had a beautiful idea. He knew that Einstein gravity is written in 4 dimensions with the 4x4 metric G mu, where the indices 1 to 4. But it was also known that the electromagnetic field is described by a factor A mu, which has 4 components. And he said, what is more natural than to add the electric field like the 5th row and 5th column? And then here, he didn't know what to put. Nowadays, people say you should put the Higgs field here, but that's very doubtful in my opinion. But anyhow, that's the only way out we can do it, or something like a scalar field. And then he had a 5x5 metric. And then he showed that if you really write the Einstein action, so that is the curvature action, in 5 dimensions, and you assume that fields do not depend on the 5th coordinate, that's what we call interpolation, then it becomes Einstein's theory in 4, in D is 4, plus electromagnetism in D is 4, Maxwell theory. So there's a beautiful idea that Maxwell theory, the theory of electricity and magnetism in 4 dimensions, is really a relic of 5 dimensions. The theory gets simpler in 5. Now, in supergravity also, the maximal theory of supergravity in 4 dimensions is such a thing. It's an enormous thing. People write 5 pages to write even the action down. It is 3 terms in 11 dimensions. Because you combine all these things as you go up. Now here you combine 2 in 1920, I believe 23 when you wrote this paper. There were 2 gauge theories known in gravitation and electromagnetism, and he saw that he could write it like this. There was another man before him. Let me just mention that because it's a nice story. There was somebody who said maybe gravity is not described by a metric, G mu, but by a scalar field, phi. And he said, in Maxwell theory in 4 dimensions is this, but maybe I add this 1 scalar field here, and then you see that T equals 5 electromagnetism gives rise to D equals 4 electromagnetism plus gravity with a scalar. Now this Mr. Nordstrom, we now know that if you take gravitation and you try to describe it as a scalar and not such a 4x4 metric, then light would not be bent at the sun. And you may have heard that people did experiments and they found that light bends at the sun. So experimentally this nice idea was ruled out, but this stated Nordstrom was a physicist, this was a mathematician. Now, the same idea, of course, would be nice to apply here. We start very high, and then in 4 dimensions, we explain all these theories. Witten, as always, made a very clever observation there's something called coset manifolds. Now I'm going only to write a curious mathematical fact. 11 dimensions, you would like to write it as 7 internal plus our 4 of our real world. But 7 can also be written as a coset manifold. Now the non-gravitational group, which in lecture 1 I mentioned was SU3 cross SU2 cross U1. It took a century to get this result. Each group has a wonderful history, full with personal tragedy and soaring drama, whatever. But I have no time to discuss it with you. This boring group is what a century gave us. Now the maximal subgroup you can write down here is for SU3 the maximal subgroup is not SU2, it is U2. And for SU2 the maximal subgroup is U1. But then there's still a diagonal subgroup you could divide here by. Now let me count. So SU3 has 8 parameters, and every parameter of the group becomes a coordinate, so 8 coordinates, plus 3 is 11, plus 1 is 12. Now this should become 7. Now this is 4, this 1 is 5, and indeed. So Witten said, supergravity 11 dimensions. Now nobody understands this, and nobody has still made sense of it, but it is a coincidence, numerical coincidence, which often means a lot in reality, but so far it's only coincidence. The maximal, the only coset manifold which has this group, and which can give 7, is the maximal coset manifold, this one. Conversely, if you believe that 11 has a meaning and a supergravity is the highest dimension where the theory exists, then you almost predict that this group has to be there. So there's a kind of interplay between these two things.
You mean there'll be some effective theory of symmetry?
Yes, exactly. And then this SU3 and SU2 will be like electromagnetism. And the gravity sector would be separate.
More than arrow, because some parameter is smaller.
Yeah, fields do not depend on the 5th coordinate, that's sufficient. Yeah. So here fields would not depend on these coordinates, for example, also. But you can also have spherical harmonics on these manifolds, and we have developed all techniques of writing this group theory. This is absolute beautiful mathematics.
There's one way in which supergravity came to the fall.
Yeah.
That's going to fit with the pattern.
Yeah. Except there was a gigantic problem. Now come to it. So everybody was soaringly happy. Except there was one observation. If you start with an d equals 11 theory, and you go to a d equals 4 theory and a d equals 7 theory, then this theory should be very small in space because we haven't seen it. That means you need a huge cosmological constant. Now the symbol for cosmological is a big lambda, so let me write lambda, I mean cosmological constant. But since there was no cosmological constant here, it turns out that you get here minus a huge cosmological constant. The same thing but with opposite sign. Now there's an enormous amount of data these days by Kobe and all these spacecrafts which are looking at the cosmological constant. The answer is the cosmological constant is practically 0. You would on the other hand predict from supergravity that it is huge, in fact huge, 10 to the 38 in order. So something is very wrong here. If there would be a lambda, that's pun was unfortunately made before by Galvan, who said there was a sign error in the exponent. Which is the same thing. Now, if you would have a cosmological constant, you could make it so big that this would be twice as big, even better, and this would be 0. That would agree. But so far, nobody has found a way of writing a cosmological constant in this highest model. I believe that there ought to be a solution, and I believe I know even what it is. And I've said this for 50 years, it's not secret, and people laugh at this when I talk about my pet theory. But they were laughing about supergravity also. And afterwards they always told me, no, we were sure it would work. So here's another one. I believe that you need to add a Chern-Simons term in 11 dimensions. which depends on all the gauge fields, and it is a generalization of Chern-Simons forms. Of course, 11-dimensional Chern-Simons form. Most of Chern-Simons theory is 3-dimensional, but here is 11-dimensional. And moreover, I believe that there is no continuous limit to the flat case. In other words, there's a parameter, the gravitational Cochran constant, and you will have terms with 1 over kappa in the action and terms with kappa in such a way that the limit kappa to 0 doesn't exist, because the terms with 1 over kappa, if kappa goes to 0, will blow up. So that would explain why everybody, me included, who first looked at the flat model and then slowly deformed it by adding Cochran constant, they missed this model. That if it is, so to say, in mathematics, it is disjunct, it is a separate island of theories, then you should really start assuming that you're ready with curving. But I believe combining these two conjectures, there ought to be an answer. And I believe that this numerical coincidence is deeper than only a coincidence. Now, I may be wrong or not, this is conjecture. So mathematicians who like to study this problem, this is a rather beautiful problem, constructing Chern-Simons theory, but it's not easy because it's not one form we are dealing, we also have 3 forms. And we have gravitational curvature, we have abelian 3-form curvature, and we have fermionic curvatures, the grafitinos. There are 3 gauge fields in the 11th dimension, that's all, but there it is. And one has to build all possible complications to make an 11 form. Now you can do it in many ways. You can take, say, three forms and 2 1 forms or whatever. And then that whole thing should be in Chern-Simons. Now, that terminates issue 2. And I have 8 minutes left. Right?
Can you do BRST?
Okay, then I'll do BRST in 8 minutes. I'll put the rest in the notes. So. At this point, I have been discussing, now I go back to lecture 3. So, 1, 2, 3, and now we're 4. In lecture 3, we discussed lecture 2, local supersymmetry, supergravity. So there was an action, S, which depended on the following fields. It depended on the field lambda, on phi, and then I introduced a gravitation field H and its fermionic part and the gravitino psi. And I'm not going to write that action down anymore, but I will call it S classical. And we had seen that that action was invariant under gauge transformations. In fact, it had 2 gauge transformations. It had local supersymmetry, but it also had local translation invariance, or diffeomorphisms. And I didn't really prove that. It's in the notes. I said you could repeat this merger procedure, but I didn't do it. So I have local parameters epsilon of x, actually epsilon of t, and lambda of t. Now, one cannot in general do quantum physics with such a classical action. Not because it's called classical, because that's the name, but there must be a better reason. And the reason is, historically, I have to race now through a set of nice anecdotes. In 1928, Heisenberg, one of the pioneers of quantum field theory, tried to convert the electromagnetic field, and he tried to look at the components of the field A mu, that is the vector field for electromagnetism, and he tried to construct a conjugate momentum for each component. The field had 4 components, so there should be 4 conjugate momenta for each component 1. And then disaster struck. He found that one of the components, A0, the one associated with time, didn't have a conjugate momentum associated with it. The technical reason was that in the Lagrangian there was no term with ddt of A0, but there it was. He worked with Pauli, another of the great of the old days, and they got so discouraged that for a year they stopped working in this field. And Heisenberg was so depressed that he went to statistical mechanics. And in statistical mechanics he invented what is called the Heisenberg chain, and yesterday the lecture of Corrigan was based on that work. That was the Heisenberg chain. This is 1930 now that he wrote a paper down, and that became Yang-Wechsler theory, and Yang of course was going to pick them up. But after a year Heisenberg saw the solution to the problem, and the solution was he would just add by hand a term. So Heisenberg added by hand a term L, what we now gauge fixing, which was little parameter epsilon. What is little, which is not my epsilon, it's another little parameter, alpha. And then he wrote d mu a mu squared, because this is ddt and that 3-4 divergence, so this term is ddt a0. Now the Lagrangian had an a0, and at the end he proposed to let epsilon go to 0. alpha. Now in German he wrote, I've prepared these letters of course, I read these over afterwards. He called it ein Kunstgriff. That's a trick in English. But then he realized that this doesn't satisfy the gauge invariance. And he called it in German Schönheitsfehler, a minor beauty. So I translated this into blemish of the theory. And violating gauge invariance in those days was so awful that he decided this was, despite the fact that he had to return to the straight and narrow path of field theory instead of doing classical mechanics, it still didn't work. So then he found another thing. Technically, that's called the temporal gauge, which Schwinger later did. But from my point, that was the wrong thing he did. Nowadays, we do add such a gauge fixing term, and we do not consider it a blemish of the theory because we've discovered something amazing. This theory has a local gauge invariance, but after you add the gauge fixing term and a ghost action, I'm going to explain ghost action in a moment, the final action has a new symmetry. It's called BRST symmetry. It is a rigid symmetry. The parameter is now not time and space dependent, it's a constant parameter. And that symmetry, that's never said, but let me say it in this elevated voice, is quantum gauge invariance. That's the word you should think. It's gauge invariance at the quantum level. Gauge invariance is a very fundamental principle we have found the last century. Quantum physics is very important. What can be more important than a quantum version of gauge invariance? BRST symmetry is quantum gauge invariance. Good.
But it's rigid.
It's rigid. On the other hand, it is in a very funny way local. Now, here the rule, what you have to do is the parameter, you replace it by a ghost field, which I will call gamma of t, times a parameter. The parameter is constant, anti-commuting, and imaginary. This is a real commuting ghost field. Here, I will psi of t, the diffeomorphism parameter, I will write it as a ghost field which is anti-commuting times the constant anti-commuting parameter. So these are the rules how ghosts go over, how parameters go up into ghosts. So on the one hand, it's a constant parameter, as you say. On the other hand, this combination is still time dependent. And here it was time dependent. So it's both time dependent, if you consider these things together, and really constant, rigid, because lambda, the parameter itself, is constant. So it combines the virtues of both approaches.
Why do you see adding this parameter field, calling it those fields, not calling it aging, just that gravity?
Yeah.
What's the distinction?
Distinction is, on the one hand, the gravitational field was present in classical quantum. The mathematical reason is that with the H field I had a local symmetry with a parameter.
What's the mathematical distinction between adding that to the field and adding this? What way is it different?
Yeah, what is different is that the symmetry changes from a local to a rigid symmetry. I would say that's the crucial point. There's a physical reason I will give you later, but the mathematical reason I would say is that the character of the symmetry changes. You extend the symmetry. Now, here we had also a rigid parameter, but then I had to drop all kinds of things. I keep the full theory, but by adding more, the symmetry, instead of staying local, reduces to rigid, with a constant parameter. Perhaps I can give you a better argument, but that is my argument at the moment. Now, where do these ghosts come from? So, Heisenberg had this idea, and you add a gauge fixing term. The gauge fixing term in our toy model is the following. Well, there are many gauge fixing terms, but the one we like, there's an observing field, d of t, times h of t, plus, and then there's an anti-commuting observing field, delta of t, times psi of t is that gravity. This is the whole gauge fixing term. I could also write time derivatives here, and that would look more like what Heisenberg and Pauli did, who also had derivatives here. But many applications in string theory do this. But some people do also time derivatives. You can do many things. And then the ghost action is just, you take this field H, you multiply it by an anti-ghost field called P of t, and then here you write the variation of H of t, And we went through what these transformation rules were, but each time you see an epsilon, you replace it by gamma, and you drop the lambda. And each time you see a psi, you replace it by c of t, and you drop the lambda. So what you then, and you do the same for the other symmetry, psi. So then you read beta of t, that's the anti-ghost field for supersymmetry, and then you write the variation of psi of t. And again, we knew this from local supersymmetry. I derived it in lecture 2, what the form was. But in that expression, you see this local parameter epsilon t, and again you make this replacement. And so here is then the full action with gauge fixing term and ghost.
What problem did you correct?
Excuse me?
What problem have you corrected?
Okay. By doing this, I now have, if I did not add this, I already did this, and this was motivated by early work, then I wouldn't have a rigid symmetry.
No, I understand that, but otherwise,
So the reason for this, there are two reasons. In practice, it turns out we like to do calculations with Feynman graphs. For that, we need to invert certain kinetic operators. If I don't add this thing, the operator has zero modes and cannot be inverted. You could invert it in the space orthogonal to the zero mode, but then
you get ready to apply a Feynman.
exactly. Exactly. The reason we do this in order to be able to apply Feynman rules. But this in turn induces this. Now in the old days of quantum electrodynamics, this was not needed, and Heisenberg and Pauli certainly were not aware of it. But Feynman, another physicist, was the one who understood that you needed to do this. And there's a very simple way you can understand it, but I will not go through that because I'll run out of time. Having now L classical plus L phase plus L ghost, the final action we call it the quantum action. This is the action we put in path integrals. When we do Wiener path integrals, we use that action. The integral over bosonic fields is an ordinary Riemann integral in the Wiener sense now. The path integral over fermions is a Grossman integral in the Wiener sense. And this complete construct of path integral we use to derive Feynman rules and do calculations. This action has now a new symmetry called BRST after the people who discovered it. And I already wrote the rule for the original gauge fields, how the BRST transformation goes. In addition, I should specify for you, when I have no time, how the ghost fields transform under these rules, and also how these auxiliary fields, these transform under this BRST symmetry, but it will be in the notes. So all these answers are unique. This is one of the wonderful things. Once you know the classical rules, all this, and once you choose this, here you have a choice. You can write it with a time derivative, you can take anything here. Given this, automatically this follows. You have a BRST symmetry. And all of modern quantum field theory and modern string theory is based on BRST symmetry. Now I should say two things. I have the opinion, and I did this very long ago, before it became fashionable, I feel that in the end symmetry will be more important than dynamics. So I believe that this kind of stuff in the end will fade into the background, and it is the path integral, the measure, which contains all physics. That certainly is not shared by most of my colleagues, although more and more we're going in the direction. We've got topological field theories, which have already not so much of the classical action. And I believe symmetries in the end will explain all dynamics, but in the context of an aspect. Now I've come to the end. I want to tell you one last conjecture I have.
in the context of what? You said in the context of it.
What is
You
it?
said you could all the come out of that.
Can't remember. Yeah.
Huh? You said aspect?
That's what I thought it said. That's matrix.
Did you say aspect?
Yeah, I'm sorry.
It's all on tape.
It's on tape. No, the last thing I wanted to tell you is the thetas we've had, and here I think some of you might be interested and help me. We have always assumed that they're Grossman variables and anti-commutator zero, but I've started in 1978 considering that's not zero, h bar, and then I wrote gamma mu alpha beta. This is an element of the Clifford algebra times, and this is x mu, the coordinates of space-time. And h bar goes to 0, you get Grossman values. If it's not 0, you get something on the right-hand side. Now, since that time, a number of mathematicians have invented quantum groups, but I would like to tell you that this is, I think, a quantum group. I was able 6 years ago to show that these structures satisfy the Yang-Baxter equation. Now, people who know quantum groups know that the Yang-Baxter equation is important. So this is not a crazy idea, it's a very deep idea. I always dream, so I think maybe one should describe a superspace not based on these Grossman variables, but on quantum extension Grossman variables. Now, people who do quantum groups hate the word h bar. They call it deformation. They don't like it. I have a very old-fashioned physical reason for doing this, and I think this is a quantum deformation. Points, due to quantum fluctuations, no longer can commute, and as a result you get this. People who do quantum groups, they usually write something like x mu commutative, so and then an R matrix and two x's. So there's always bilinear on the left and the right-hand side. Here, however, bilinear goes over into linear. This I would associate with the notion of curvature on a constant manifold. And this I would like to associate with the notion of torsions. It so happens in supergravity that you need both torsions and curvatures. When you do superspace, the people who know that, they spend a lot of time in analyzing simultaneously curvatures and torsions. I think at the quantum group level you also need torsions in addition to curvatures. I did show it to a lot of the people in the field, there, Manin, others. I haven't been able to convince them it's interesting, so I'm working on it. Maybe some of you are less resisting such unorthodox ideas. And I believe from the models I do that this is very interesting. Thank you very much.
Questions?
I never understood the use of English by physicists. For example, in mathematical symmetry, here I would ask you a question about when you use those additional terms for the gauge fix, those gauge fix what do they fix? Do they
break
this in which sense?
Do you repeat the question? The question was, when you add gauge fixing terms, what do they fix? Maybe the better word would be gauge breaking terms. What they do is they break the local symmetry. And that's why Heisenberg and Pauli said, this is a disaster, we should do that. Probably people felt that this puts the field in a bad name and they changed it to gauge fixing. But the natural result is that after you add that term, your local symmetry is gone. It is just as bad as anything random you would write down. But then, if you add these ghosts, you get something back. That is that rigid view. Okay, that will come. Yeah?
You emphasize that the BRST symmetry replaces the local by the rigid.
Yes.
On the other hand, at the very bottom, under new BRST symmetry, we've got it in terms of the ghost fields, etc., which are time dependent.
Yes. So let me write entirely. So that's a good question. So let me write one more. The question is, this is a time-dependent field, and how can that still be in rigid symmetry? I'll write the answer down. It is Ct, C dot T times lambda. So it is non-linear, first of all, two C's, 1 into 2. But the parameter lambda is still a constant parameter. In that sense, it is rigid. If the parameter would have been a function of t, then I would have called it local, but it isn't. However, as I would like to stress once more, because you always get this combination, it is both rigid and local. The parameter is indeed rigid, but the combination is still arbitrary t dependent.
Other questions? Okay, let's thank the speaker again.